Hello, in this video we're going to talk about simplest implementation of the PID controller in the Python program by showing its effect on the simplest model of an airplane. And the first question that is usually comes to mind is what the relation between the PID controller with in Python with the airplane to the ESP IDF environment that we usually talk on this channel. You will see that the Python program doesn't use any special fancy libraries. It's only hard-coded with very simple lines, and if you will understand the principle of the PID controller, you will easily implement it for your needs in the ESP32 in C language. Okay, our program will create this screen, the blue one that you can see on your left side, where the airplane is modeled by the triangle, where you can change then the alpha angle, which means the alpha between the airflow and the airplane itself. And on the left side of the screen, you can see different data, physical data that the airplane is experiencing, like velocity and different forces like drag and lift forces. When we are talking about PID controller, this controller also considers proportional integration and derivative of the physical world. So he sums it up in a way that allows you to give different weights to each part of the controller. We will compare it to the handheld controller with the simplest controller with like a Bing Bang mode with a plus and minus, and finally we'll show the PID controller in this program. Regarding our physical model, we have the simplest airplane model where we have thrust, drag, lift and gravity. And we are changing only the alpha, only the angle of this triangle of this airplane relative to the airflow. Our control loop, it looks a little bit difficult, but it's actually very simple. We want our Vy, the speed on the height measurement be 0. So we are looking to have a trim flight, a very straight line flight, and not like a sinus or some control flight. So you basically want to fly in the airplane in the straight line. So in the beginning, we want our Vy be 0. So if Vy is not 0, we will change it in some way. In order to change Vy, we need to update our alpha angle, and then we will go to the physical model and once again and see all this iteration on the screen. Those are basic aeronautical equations. I will not go into it. It's just to model the physical model of the airplane. It's not really related to our main point of this video. And we will compare 4 cases in order just to see the differences in different control parameters. First, we will see that our physical model is valid. So we will switch off the thrust of the airplane, and we will expect a free drop of the airplane, like a rock, basically. And then we will implement the manual control. So we will try to control the airplane by ourselves. So we'll change the alpha angle manually. Then we will use the simplest Bing Bang control. So if the Vy is positive, we will reduce the angle, and if Vy is negative, we will increase the angle. And after it, we will see the PID controller implementation and see the difference between all those cases. As always on this channel, we have our code saved in the GitHub. You can see here Sims IoT devices. Inside repositories, the PID controller Python repository, where you have only one Python file, which you can copy in its very short file, relatively, which you can copy to your editor and run. So that's what we did. We copied this file here to the VS Code editor. Before we will start running it, let's go over this file and see what we are using. The main thing that the only library that we are using is the Pygame library, just in order to visualize the results. And we also use a mass library for some easy calculation, but those are very standard libraries. And without visualization, you can easily implement it in the ESP32 environment. So we initialize our graphical environment, define the screen, different colors, and different constants for the physical model, also the clock. And then our main part of this program is the aircraft class, which defines the aircraft. Here we have different aircraft constants, which including the position of the aircraft, the velocity of the aircraft, the alpha, the aircraft angle, the main parameter, mass, thrust, and so on. We have different airflow parameters like CL, C lift, and CD, C drag, which are very common in this kind of calculation. And those three are PID parameters. You can see it here. Those parameters can define the proportional integration derivative controller modes. You can see the different weight for each part of this controller that we will use later on. Here is the function which calculates the forces. You got the equations in the presentations before it with the lift and drag forces and also the gravity. This is the most important function of this program, where we have three controller implementations. This is the first controller implementation where we control it by hand, by pressing the left and right buttons on our keyboard. The second controller implementation is so-called Bing Bang implementation, where we see the error, an error in the velocity, and then add or reduce the angle without any considerations regarding the size of the error and so on. And here you can see, and that we will talk about it later, the PID implementation, which consider different parameters like Kp, Ki, and Kd, so to calculate the best correction for this problem. We will talk about it later. So going on with the program, we calculate the forces with the previous function and transfer the angle to the radians, and then calculate the thrust for Fx and Fy forces, because it's a two-dimensional problem. acceleration, so that's the basic physics basically. Update the velocity, update the position, and put our plane on the screen. Also, we update the coefficient of lift and drag. And this function here, we just draw the updated model with updated data on the screen. Here we draw our airplane, which is a triangle, and print different data on the screen, like alpha, different velocities, different constants, different forces, and so on. So if you are a little bit more interested regarding this implementation, you can just feel it more deeply. Let's put it this way. Okay, that's basically it. And here we initialize the aircraft model and start to run our program, which is a few line program. When we initiate the screen, initiate the ability to read the keys from our keyboard, we update our physical world, we draw it on the screen, and after a small delay we do all over this process again. Okay, so here is our program to work with. Okay, let's run this program and see what we can do with it. Now I'm not pushing anything. You see the airplane is flying with thrust, and he's just falling because it is not controlled. So let's go to our basic goals and see if we will remove the thrust. Here I will put the thrust 0 and switch off our initial thrust. Save it, and here, okay. Here our airplane, you see Vx is 0 and Vy is growing till it's falling. Okay, the alpha is 0, so it's basically just felt. So we have a little bit more insurance regarding our physical model that it is actually working. Now let's put back the thrust and comment it. Okay. Now I will try with the thrust of 7,000 newtons. I will try to fly this airplane by myself. So you see here, this block is just reading the angle from my keyboard and increasing the angle from small quantity. Let's run it. Okay, so you see my alpha is bigger, so I'm trying to get up. Now it's smaller. I am going down. I'm also going up, and I crashed. And of course, after some practice, manually you can do it much better. But the main idea that it's a pretty difficult task to control this system manually. Okay, now we will comment this section and uncomment this section, which is, I call it a Bing Bang navigation. So it will automatically see the error in the Vy, in the height velocity. And if the error is 0, so we have a negative velocity, we will up our plane. The angle will increase. If Vy is positive, we will decrease our angle. So we will want this plane to fly in the constant path. Okay, let's run it. Okay, you can see it's alpha automatically moved, and the plane is moving pretty good. You see it stays on some in some margin here, so it succeeds in its mission to not to crash, but you can see the flight is pretty bulky. So this controller is not very smooth, but it's roughly working. I can say if you will leave this program for a long time, eventually it will crash because it's can see any integrated errors. So in some eventually it will crash. You see, it's like right now is lower that we have started and so on. I will close it. Now let's employ our PID controller. So it's the main idea that we have in this video. This is our PID controller. Okay, I will explain it a little bit later. Now let's see just how it works. So the PID controller is succeeded to maintain pretty smooth flight. You see, alpha is almost not changing, and the velocity in y direction is basically zero. We have a thrust, so we have an increase in x, and the drag is rising. So at some point it have to update itself. So we have pretty smooth alpha. It's not perfect, but it's considerably better that we have in the previous controllers. So you can see with a few lines of code, we have a pretty good controller that can converge the system in a pretty good work regime. Okay, I will close it. Now let's go over how it's implemented. First, we see the error. The error is any value of the Vy. We want Vy basically be 0. First, we integrate it. We integrate our error and see it on the with relative parameter on the here in the final stage. Then we derive the error, and we add all those data to the output. The output is the output of Vy. This is the correction of Vy that we want to achieve. Here we transform our Vy to the required angle in order to achieve this correction. Please don't put it too much thought why this output is divided by 10. In the real world, we will have to develop the equations and calculate the relation between the Vy and alpha. Those equations will be pretty complicated, and in order to simplify this video, we approximate this result by simply divided by 10. It's approximately good. So the main idea here is to transform the Vy output required to required angle. When we have a required angle, we update the angle of the airplane, and this is the angle that need to be implemented in order to continue the flight in straight line with minimum divergence to this needed. in order to summarize, I will run it once again. We have the basic airplane model with the PID controller, which is implemented only with few lines of code without using any kind of special libraries. And you can see that this controller is working pretty good relatively to our hand managed controller or the Bing Bang, the simplest controller that was implemented. So the PID principle is really work. So now, if you want to implement the PID controller in the ESP IDF environment, the only thing that you need to use is those few lines of code, which can be easily implemented in the ESP IDF without any libraries. Thank you.